introduction. It's really great pleasure for me to be here and see so many people that I know actually, but also seeing many new faces. And so it's really hope to have a lot of interaction here. And the title of my talk here is, I would say, not so much the title of my talk, it's more how I would describe here this workshop here. And so I have prepared here the slide just before yesterday to pick up a couple of buzzwords that I found in the titles that highlight a little bit the vast variety of materials and phenomena that we can looking at with near-field microscopy. And so this is really amazing. So I think we never had thought about that impact of this tool when we started at NeoSpec. And so I divide here between materials research and nanophotonics applications. And here particularly this materials research part I think is really growing a lot. And I found here from solar cells to Alzheimer's, so really a lot of things. I think that's really a big future here. On the other side, we have here a lot of nanophotonics applications. This is something that was growing, particularly with polaritons, quite largely in the last years. Also, the majority is really in material sciences here. And so in my talk, as I'm the first one, I would like to introduce the technique a little bit, but also try to connect a little bit the methodologies in differences and similarities. How can it be that by light scattering at an AFM tip, we can see so many different things, and what does it mean? And so that's the outline of my talk. So I will start with an introduction, which also has a little bit of tutorial aspect. Could be a little bit longer, and then I have chosen 3 topics, 2 of them that are unpublished and ongoing work. What I introduce here, demonstrate a little bit by looking at molecule intercalated molybdenum disulfide, where we map molecules and conductivity. Then in the second part, a new conducting polymer, where we map the Drude response. And then in the last part, if time is still okay, then I will talk about polaritons and how they interact with molecules. So I try to cover everything a little bit. If I don't manage this one, there's a poster by André Billinkin. He will talk about the details on this. All right, so let me start at the very beginning, as I'm the first speaker. So the technique that we use goes back actually to the early 90s by Vikramasinghe, Bokhara, and Kawata. They introduced nanoscale light imaging by using an AFM tip, shining light on the tip, and then collecting the backscattered light. And then by recording these lights simultaneously to topography, we get nanoscale-resolved images. So this was then picked up by Fritz Kallmann around 2000, together with Bernhard Knoll. They had this really seminal paper where they showed the first infrared spectroscopy contrast. I think that was really the beginning of what we nowadays call s-SNOM. And I was really glad to join Fritz actually and his team in this moment. And from then on, we developed a couple of techniques and methodologies that actually form now the basis of what is a typical s-SNOM setup. I want to briefly outline this. I guess most of you know it, but nevertheless, there may be people who are not so familiar with it yet. So we use standard AFM tips. We operate in tapping mode, which means that the tip is oscillating at the frequency omega. Then one of the key features is that we use a parabolic mirror that accepts nearly everything from visible light to terahertz, even microwaves. So we use different lasers, focus it on the tip, and then we collect the backscattered light. And now there are 2 important features. So first of all, we use an interferometer, which allows us to measure amplitude and phase, which gives us access to both reflective and absorptive properties. And further, we can use this interferometer here as a Fourier-transform spectrometer in case we use here a broadband laser source or a synchrotron. So that's really important, this interferometer. And the other thing is that because we operate here in tapping mode, we have the possibility to measure here at a higher harmonic, a multiple of the driving frequency. And that's another key feature in combination with the interferometer, because it allows us to extract the near-field scattering out of a huge background signal. So these are the key features. And so now I would like to distinguish a little bit the basic mechanisms that we have. Let's start with this here. Typically, we use metal tips, AFM tips, and we can use them, for example, for material contrast imaging. And in this case, the tip is kind of active. It acts like an optical antenna, focusing the light to a nanoscale light spot here. That's why, in principle, one could call it tip-enhanced s-SNOM or tip-enhanced near-field microscopy, very similar to tip-enhanced Raman spectroscopy. So that's why I also have here active. The role plays here an active. The tip plays an active role. So how does this work then? Okay, so here's a simulation that shows what happens if we shine here terahertz light on the tip. we polarize the tip here, and then we get here, we can describe this by a dipole. Light comes in, light comes out, and this tip scatters, and on top of that, it produces a near field. The near field is just hanging around here, not doing anything if we are far away from the sample. So now this scattering here is massive, and actually this is a dominant part of what we call the background, actually. Now, if we bring this tip closer to the sample surface, then these near fields reflect back to the tip and induce an additional dipole in the tip here, which scatters. And it's elastic scattering. Nevertheless, I make it in blue so that we can distinguish it. And this blue light here, which has the same frequency, that's the near field scattering. That has the information that arises from the near fields being reflected here at the sample surface. And this near field reflection depends on the dielectric function here. And the near field reflection coefficient in the electrostatic limit can be described by this factor beta here. So that's it, the near fields reflect, and through that we get into the light information about the permittivity of the sample here. So that's what we use for material contrast imaging. However, then there's a second big application, and that's we make, again, use of metal tips, but now the near fields do not only reflect, they also have the possibility to launch electromagnetic waves that propagate along the surface here if the material hosts such surface waves, polaritons, for example. And one of the most famous examples, probably graphene. So the tip now launches these waves. We wouldn't see them, but eventually we probe close to an edge or a defect, and then these waves, they propagate towards the edge and then they back reflect. And at the position of the tip, they interfere with the incident field. And that gives rise to interference fringes that we see here, which are on top of the material contrast. So here we see graphene on silicon carbide. We see here clearly a material contrast. We have different brightness here in average. But on top of this, on the graphene, which only the graphene is supporting the surface waves, has these fringes here. And from these fringes, we can directly measure the wavelengths of these polaritons here, 40 times smaller than the incident wavelengths. So s-SNOM is here the only possibility to really map that in real space. So here we have the tip, again, being active, and we have this tip-enhanced effect. Then there's another methodology that we could use, and it's maybe not so much used, but very often we have samples that by themselves produce a strong near-field distribution. For example, metal antennas here, metal rod. And in this case, we are eventually interested in not mapping material contrast, but the field distribution that is created by this dipolar antenna, which is indicated here by field lines. And now we stick in the tip and we scatter out the near field. And to do so, we want to be minimal invasive, and we very often use silicon tips, for example, or we operate such that the tip is not strongly interacting with the sample. So that's important here because we are interested here in the fields. And that's here a gold rod, and you see the gold rod is pretty inhomogeneous. This is all gold. This is not material contrast that we are seeing here. These are two bright spots. They reflect here that we have a lot of field on the extremities of this antenna here, right? And that these fields oscillate out of phase if it's an out-of-plane component that we measure here. So that's near-field distribution mapping, I would say. And if you place such an antenna on top of a material, here as an example again, graphene, that hosts surface waves, then not only the tip can excite these surface waves, but it can also be done by the near fields of this antenna here. And then the antenna is excited, it launches these waves, they propagate away, and now we use the tip and scatter it out. And that way, it's not the tip that launches and we see back-reflected waves. No, here we see antenna launch waves, and then we pick it up with the tip. And that way we do wavefront mapping. Yeah? And that is conceptually rather different here. So that's something that is particularly in polaritonics and nanophotonics, something that we use quite often. So now I want to start with this material contrast imaging, and because I think this is a really the biggest part of applications for the future. And I have here the slide, which is a little bit complicated. I don't want to go into detail. I just want to say that there are different ways of describing the scattering. So that's what we need to do, or need to, in the beginning, to understand what is going on. So we are interested in finding out the scattered field. How does this depend on the sample surface? And in the end, there are different equations that connect the scattered light with this permittivity, the dielectric function, which is a complex number here. And essentially, what we find is that the scattered field through this near-field interaction depends on this near-field reflection factor that I mentioned before, so how strong the near fields produced by the tip reflect at the sample surface. And that is exclusively here in the electrostatic limit a function of the dielectric function here, right? So there are different ways. The finite dipole model, which is qualitative, the point dipole model, sorry, the finite dipole model, which is rather quantitative, and there are many more models. Dimitri Basov's group and Misha Vogler, they developed a lot of models. So there are many of them. This is just our own, and I just show them here. That reason. Now, I prepared this slide here, and I would like to connect now all type of applications and fields, and to that purpose, I created a virtual material dielectric function that covers a lot of things. So this is the permittivity, and then let's assume this material is semiconducting or metal, and I put here a lot of carriers in there, and this response in the permittivity function we can describe with the Drude term, for example. But then eventually, this material is a crystal, and it hosts crystal lattice vibrations, phonons, which are very strong, and I describe it by a Lorentz oscillator, and I mark here, I call it strong. It's very strong because the permittivity becomes negative here in this region between the transverse and longitudinal optical phonon frequencies, similarly to the metal response of here, this Drude term. And then we potentially can add here a Lorentz oscillator that describes molecular vibrations. This is a weak oscillator, meaning that the real part of the permittivity is always positive. So also excitons, for example, could be described. So I think these are just some representatives for different excitations and different materials. So with this here, we have semiconducting materials, crystals, minerals, polymers, whatever. So I put this all together here, and I separate them spectrally so that they don't overlapping. But as we will see later on in an example, these excitations can overlap, and we can probe them eventually in the same spectral range. So that's the dielectric function, and now I asked Lars from a PhD student to do a calculation that includes the modulation, demodulation technique, amplitude and phase resolved measurement, and we use the finite dipole model for this, and this is the result here. And we see that there are similarities and differences for these different oscillators. So first of all, let me point out that the amplitude has this typical behavior. We have this dispersive line shape with a maximum and minimum, right, for all these three oscillators. And the phase always has a peak here. And so there's some resemblance between the real part and the imaginary part of what we measure with amplitude and phase in the S-NANO signal. So if you look at the Lorentz oscillator, then we see actually that the amplitude corresponds pretty much to the real part, and the phase corresponds pretty much to the imaginary part. And the position where these resonances occur are pretty much co-located. So if you are just, let's say, interested in chemical composition and want to know, is there a peak or not, then we don't need to do even a lot of modeling. So we get pretty much the standard response of this material. This changes, however, quite significantly if we go to this strong oscillator or Drude, because now we see that the response here observed in the SNOM is frequency shifted compared to the resonance that we see in the dielectric function or in the far field. And the reason for that is, I mean, it also happens for the Drude oscillator. And the reason is that here in these regions we have the permittivity close to -1. And in this case, this reflection factor beta, this near-field reflection factor beta becomes larger than 1. So a far-field reflection coefficient never becomes larger than 1, but in a near-field this is possible. And so we get a resonance, and this resonance does not occur at let's say, the phonon resonance, but it occurs here where epsilon is -1. And this corresponds to a tip near-field induced polariton resonance. And that, I would say, is pretty fundamentally different to a far-field spectrum. With far-field, we cannot excite that, right? But with near-field, we can. And first of all, the advantage is that these near-fields are very strong. They can be up to 10 times stronger than that of these weak oscillators. On the other side, we now need to do a little bit of modeling because interpretation is sometimes a little bit more tricky. So yeah, with this, I wanted to show that in principle, we can connect here with this response. That's what we see in biology or in life sciences here, if you look at minerals, and here, if you look at semiconductors, and all can be described really in this kind of nutshell-like picture here. So now let me give you an example where we actually see a combined Drude molecular response, and this was done in collaboration in-house at Nano Gune with colleagues who intercalated molecules into molybdenum disulfide. And they did that because they wanted to make it conductive, and actually it turned out that it becomes even superconductive, putting organic molecules into this MOS2. And however, this superconductivity were only partially achieved, and so the question arises, So what is going on here? And so we thought, let's make a local conductivity mapping, and we can do this with s-SNOM. So what we did is we exfoliated this intercalated material and put it on a gold surface acting as a reference. That's a cross-section. And then we imaged at terahertz frequencies, about 2.5 terahertz, 84 wave numbers, and then at 2 infrared frequencies, and we have amplitude and phase here. And we see that this material is as bright as gold in the terahertz, and then the signal drops down, which is already a little bit indicative of a Drude response. And in parallel, we don't see any phase contrast in the terahertz, and then phase pops up here at these mid-infrared frequencies. So all that is already indicative of a Drude response. So we confirmed that by taking nano-FTIR spectra here, done with the supercontinuum infrared light source at 3 different representative points here. And we put this now together with the measurements from the terahertz. So we see here this spectral decrease in the amplitude, and we see that here we see some kind of maximum appearing in the phase here. And this is completely different to, let's say, pristine MOS2, which just was exfoliated without any intercalation, so we get a totally flat response in amplitude and phase. So that's clearly something going on that we can relate to eventually a Drude response, free carriers introduced by the molecules in this material. And so that's what we did. Then we used, again, this finite dipole model, and we've tried to fit these spectra, and this works pretty nicely. And we used here the Drude response to describe the permittivity function. And then we can fit this rather nicely. The only problematic point was here P2, because we see that even at terahertz frequencies, we have here a signal that is significantly smaller than 1. Also, we see here a variation of the signal. So that we cannot explain by a Drude response. So after some careful analysis, it turned out actually that we can describe this response here by assuming that we have here a vertical change in the carrier concentration. If you assume that we have here material of a low carrier concentration on top and below something of large carrier concentration, then we can nicely match this here. And so that's our interpretation. For example, in these black areas, we see here that we have obviously undoped areas being consistent with undoped areas. And that's probably the reason why superconductivity in this material was achieved only partially. But that's ongoing research, so it's all a little bit speculative at this moment. So from that, we can then extract carrier frequencies or carrier concentrations, and we see that it varies in the doped areas about 50%. And what is also nice, we can extrapolate the DC conductivity that we would measure by transport measurements in average, and we get here numbers of about 500 Siemens per centimeter, and which matches actually quite nicely with the far field, with the transport measurements. What is also nice here is that if you have a closer look here, we see this feature here, sharp feature, dispersive-like, and here a peak, and that's the molecule actually. And what is nice here, so we see now this molecular response on top of the Drude response, and we now can correlate the strengths of this molecular peak with the strengths of the Drude peak, and we see there's a correlation. We see whenever we have more amplitude and phase signal here, a stronger Drude response, we have more molecules, or more molecular signature. And from that we conclude that this inhomogeneities in the conductivity comes just from an inhomogeneity in the molecular distribution. And so that's a little bit our hypothesis here, but as I said, this is some ongoing work that we need to finish to write up. Then another example, again back to conductivity. That's just happens that we have a lot of projects in conductivity mapping at the moment, and this is done in collaboration with Xianling Feng and MPI in Halle, and they are. I'm not supposed to talk too much about the material. They were able to synthesize a new polyaniline material, which is a two-dimensional polymer, which is conductive. And at this moment, these flakes grow only in the size of 10 to 20 micrometer. And they were interested in checking what is the conductivity, which was a bit tricky in the beginning because hard to connect these organic flakes. On the other side, they tried terahertz far-field measurements. We tried infrared far-field measurements, but these flakes are simply too small. So near-field microscopy is an ideal tool. And so here I show you the results. So we took doped PANI on this side and undoped PANI on this side. And we see a terahertz image, again, 2.5 terahertz, and then in the infrared. So this PANI, this conducting polymer, is as bright as gold, all the way to the mid-infrared. So it's highly conducting. However, if it's de-doped, we see that it's completely dark, right? In the terahertz as well as in the infrared, which is a clear indication that doping changes contrast massively. And so we did the same game as with the molybdenum disulfide. We took a large set of images, here amplitude and phase. Here we use pseudo-heterodyne technique, and which is a little bit harder to implement in terahertz. Here we used what we call synthetic optical holography. And we get nice amplitude phase images in the terahertz. Should mention we use here a gas laser and a bolometer, otherwise it's hard to get such good images. And then we see here again this decay in the amplitude signal and the increase in the phase signal. So we combined everything here together. So it's a set of measurements, quite complicated to put this all together with such a spectral range. So we have here terahertz monochromatic image data points. Then we did nano-FTIR with a mid-infrared supercontinuum, and here we used an infrared, more near-infrared continuum. And so we put this all together in amplitude and phase. In red here, the data obtained on the doped PANI, and the black data here on the pristine PANI. So here we see flat response, not much is going on. Here we see eventually some peaks that relate to the molecular vibrations of this PANI. But more important is here we see again, we can fit this very nicely with the Drude response here. We see the amplitude decays and the phase has this maximum here. So we take the finite dipole model again, we use here Drude response, and then we can fit this, and we get here carrier concentrations that are pretty high in the range of 10 to 19 per cubic centimeter. And what was more important for our collaborators was they wanted to know the DC conductivity. They were not so much interested in the optical properties on the DC conductivity. And so we can now use this dielectric function and convert it with our standard equations into conductivity, and then we can extrapolate this actually to DC. And that way we got a conductivity of about 170, 180 Siemens per centimeter, which again, in the meantime, collaborators managed to also do transport measurements, and it's a pretty good match here. Nice advantage here is we really can prove that it's a Drude response because of Drude behavior, and we can do that without any current, without any contacting of this material. And I think that's some really interesting new application looking at conducting polymers in combination with molecules. I think there's a lot one can learn. All right, so with that I would finish this materials part. I don't know, Adrian, how much time do I have? 10 minutes? Okay, good. Right, that's enough. Okay, so then let me come back to polariton imaging. So that's now from material science, as said, where we look at local properties that are encoded in the refractive index. Now I will come to this polariton imaging, mapping electromagnetic modes. And just as a reminder, we have here two possibilities. We can either use the tip to excite these polaritons, and then we measure what is back reflected, or we use structures where we can excite polaritons and then we pick them up with a tip. And what are these polaritons? So the first one here, and many people are maybe from other fields. I want to briefly introduce it. That's a very nice review paper that I took this figure from here, from Dimitri Basov's wrote this. It's really very nice. And it summarizes here all these polariton waves that we can have in 2D materials. They also exist in normal materials, but here it's focused on 2D materials. So what is it? A polariton is an electromagnetic wave that is formed by coupling of photons of light with dipolar excitations in the material, for example, with charge carriers or plasmons. And in this case, an electromagnetic wave is formed that is called a plasmon polariton. And the fascinating thing about that in 2D materials is that these polaritons, they have an extremely short wavelength, and they have extremely large field confinement. So here, that's schematically shown half the photon wavelength, and that's the wavelengths of these polaritons. And that makes it interesting for future nanophotonics circuitry or for sensing applications, for many things. That's why people are interested in imaging them. And as I said, there is the s-SNOM that can image that. In the meantime, with electron energy loss spectroscopy, one can image them, but I think s-SNOM is a really quite useful tool for this. Yeah, then we can also couple light with crystal lattice vibrations. Then we get phonon polaritons in crystals, like in polar crystals like hexagonal boron nitride. If you go to semiconductors, we can get exciton polaritons, and in superconductors, Cooper pair polaritons. I think they haven't been seen yet, magnum polaritons, and so on. So yeah, these plasmons have been widely measured. That was here a plasmon polariton in graphene. And I want to now focus a little bit on phonon polaritons in hexagonal boron nitride. Here, I think you have really many talks on these polaritons, so I jumped directly into the work that we did. And we were interested in how does these phonon polaritons that propagate in an HBN slab interact with molecular vibrations. Why that? Because these modes are so highly confined that there may be a very strong light-matter interaction, strong light-matter interaction in the mid-infrared has attracted a lot of interest recently because it was let's say reported by Thomas Everson's groups among others that this strong light-matter interaction with molecular vibrations eventually can change chemical reactivity rates and landscapes. So it's fundamental work here. We just want to see how is this interaction. And we use polariton interferometry for this, where we place the HBN on top of molecules that have molecular vibrations in the mid-infrared. And that's a simulation that mimics the tip as a point dipole, and this tip now is scanned here. What we see is that this dipole excites a wave. This wave propagates along the slab until the edge here, and then it propagates back, and then we get these interference fringes here, right? So if the tip is in a position of very high intensity, then we scatter a lot out, and then we get a lot of backscattered signal. Now what we see here, that these fields penetrate into the molecular layer here, and so we can expect that the molecular vibrations eventually interact with the polaritonic field, and then some interaction may happen. And this is what we wanted to study, and I show you here first a result where we did nano-FTIR. So what we did is we scanned along HBN. First, we started with a pure HBN, and we scan it perpendicular to the edge, and then we record spectra at each pixel, and then we get this frequency spatial map here, in which we see these fringes here. So if you had a fixed frequency, we see here these oscillations, and this is the polariton that propagates in this direction. Now what we see is that with increasing frequency, this fringe spacing, which corresponds to half of the polariton wavelengths, it shrinks, and that's a typical behavior for polaritons. And very often we are interested in learning about the so-called dispersion of the polaritons, which is the frequency versus the wave vector or the momentum. And having such an image, these are really raw data that comes out of the microscope or the nano-FTIR setup. We just need to Fourier-transform along the spatial coordinate here, and then we get immediately the dispersion. And now this is the dispersion that we see. Actually, we see here on the other side two dispersions. So do we see two polaritons here? No, it's one and the same polariton. And we can understand it, if you remember what I said before, the tip can excite these waves, they propagate towards the edge, and then they propagate back. And that would be this branch here. While the incident field can also couple directly at the edge into these propagating waves, and then they propagate to the tip and are scattered out. So the polaritons that are excited here propagate this distance once, and the tip launched twice. So the apparent momentum for tip launch polaritons is twice as high as it is in reality. And that's why we see here two dispersions indicating two polaritons, but in the end it's always the same polariton. It's just they propagate different distances. So what I want to point out here, these lines here are really smooth. There's no interruptions, nothing, neither in the real space image nor in the dispersion. And this changes quite significantly. But somehow this is blocked now. Cannot move forward. Is there any? I have the feeling this computer crashed. At least it's frozen. Can somebody check this, please? I don't know what is going on. I cannot. No, it's okay. Good. Okay. No, thanks. Good. Now we place the HBN on top of the molecules, and that's the far field spectrum of these molecules. We see here this molecule is called CBP. It's an organic semiconducting molecule. And we see here a couple of absorption peaks here. And we see now that if we repeat this experiment, we see again these polariton fringes and interference. But we see this interruption here, which happens. It's an interruption and bending of these polariton fringes here at the positions where we have these molecular vibrations. So obviously we have here something going on. The polariton both the polariton launched by the tip as well as the one launched at the edge, they seem to feel the presence of these molecules, and we get here kind of an interruption wherever we have these molecular vibrations. Now, we try to analyze this data. I have to say the data are not, let's say, in this data set were not good enough to really make a quantitative analysis, signal to noise, spectral resolution, and so on. So we zoomed into here, but with the help of monochromatic imaging. And so we do a classical s-SNOM image. We come with a laser, and we QC, a quantum cascade laser, and we scan perpendicular to the edge here, and then we see these polaritons, but at now one frequency. And then we do this at different frequencies across this molecular vibration here. And what we see now is that with increasing frequency, these fringe spacing becomes smaller, the wavelengths become smaller. That's what we expect from a polariton. But then in the region of the molecule, we see that the opposite trend happens, that the wavelengths become suddenly larger. And this is known as anomalous dispersion. And then after we are crossing the molecular vibration, we are going back into again, the same behavior. So normal dispersion here, and here anomalous dispersion. That means that the wave propagates here with negative group velocity, for example. So this is all interesting fundamentally. Now we can do the same. We can now Fourier transform each of these line profiles, and then we get a dispersion map here. And so we get here frequency versus momentum. And without going here too much into detail, because Adrian is standing up already, I think I should speed up. So from that here, we can extract profiles, for example, vertically at a fixed momentum, and then we can determine the eigenmodes from these diagrams. If you want to know how exactly, then please go to the poster by Andre. And we can fit this with harmonic oscillators and can actually find out that these two modes that we can describe by two coupled harmonic oscillators, they really coupled so strongly that new eigenmodes emerge, and so we are here in the regime of strong coupling, and that could be it's fundamentally interesting. As I said, that's not really an application here. We use the microscope to study a very fundamental effect. Then just let me finish with a couple of overview slides. There's a couple of other things that one can do with this technique. So here, this is all a hexagonal boron nitride, and with it, we found here modes that propagate inside the slab. We also found modes that propagate along the edges here. They have a shorter wavelengths. Here we then use this norm to demonstrate that if we can make waveguides, we cut them into small stripes. And we saw here that we are cut-off free, so we can make stripes out of HBN that are more or less a nanoscale thin, and we can still guide these polaritons, can make metasurfaces and so on. So don't want to go further detail, so maybe this as one of the last slides. So I think I hope I could illustrate a little bit the different possibilities and how they are related to each other by light scattering from an AFM tip, how we can get here interesting applications in various different fields. I said here another example, this is mapping strain fields via tip-induced phonon polariton spectroscopy. Then we will hear, I think later on, there are a couple of talks I saw on bioimaging. Here that's a spectrum of proteins where we see the amide1 and amide2 band, and from that eventually could studying misfolding processes. But again, this here all is encoded in the dielectric function and could be described with a slide that I had before. And then this is an example from where we looked at transistors from real devices, some years old. That's why they're very big, but we can map carriers in transistors, and then the polariton mapping. And so far this was all elastic light scattering with CW laser. Just have this slide, which actually an older version from a slide that I borrowed from NeoSpec. So this is what is ongoing here, and I think I covered a little bit the nano-FTIR and this polariton interferometry. But of course, this can be combined with synchrotrons. We have lots of experts here who will talk about this. That what is also ongoing, and I think a lot of potential, is combining this with ultra-fast pump probe. There will be talks too. Low temperature is something that is emerging. And terahertz time domain spectroscopy, what I showed is CW laser imaging with a gas laser, but TDS would be definitely interesting, but I think it's still a little bit tricky. And with that, I would like to finish, and maybe with this historic slide here, I think s-SNOM is really an emerging trend, but that was not always the opinion. So I have this citation here from Albert Einstein. He said this, that he thinks that is an unusable technique, and he said that not to s-SNOM, because he said it to this idea from an Irishman called Edward Finch from 1928. And that's a drawing that was never published, but it was found by Lucas Novotny in the Einstein's Museum. And then Lucas published it. And what he described, and it's pretty amazing, he said, let's take a gold nanoparticle and scan it above a tissue cross-section. And then we create here an evanescent field. The evanescent field is illuminating the particle. And then this particle, if it hits some obstacle or if you scan something around it, this evanescent field will be scattered. And so the idea was to collect that and then scan this. So we had this many years before the STM, nanoscale scanning, light scattering from a gold nanoparticle and collecting it. So he invented here the scanning probe microscope in the optical range here. But then, yeah, he sent this to Einstein, and Einstein replied him this, and I think at this time it was pretty clear that this is difficult. And so Sünch came up then with a revised idea where instead of a gold particle, he said, let's squeeze the light through an aperture, because then we don't have the problem of the background, because background was actually what Einstein said could be the major problem. So he published this here, and then it took quite a while, until 72, until this was published. And then there were many further obstacles, and finally we are back to, in principle, this idea here. And thanks to, let's say, all this modern nanotechnology and developments, we are able now to really collect this tiny little light scattering from particles. We are doing it with a SNOM, with a tip, because it's a little bit easier. But in the end, I find it really fascinating. This idea is really old, 1928. And with that, I would like to finish. And thanks for your attention.